Hello everyone, welcome to the station for fluid mechanics. This is week 6. This week we will have 7 questions and we will get started with the first one. This is question 5.7. So we have a pipe with a 21-inch diameter. So we have D is equal to 21 inch. And this is carrying a water having a velocity of 10 feet per second. So what is the discharge in cubic feet per second, and also gallon per minute? And also in the question, it is given that 1 CFS is equal to 449 GPM. So we have very basic but powerful equation, which is continuity equation. Q, which is flow rate, is equal to velocity times area. So this is actually coming from very complex equations, but eventually this is the final one. This is the final version, and we are usually applying this. So when I say basic, it is very short, but as I mentioned, it is coming from other equations. So to find the flow rate, we have velocity and we need to find area. So since velocity is given in feet per second, we can also convert this diameter from inch to feet. So it will be 1.75 feet. And since this is a circular pipe, the area will be pi d square over 4. So if you substitute all these values into this equation, we have 10, which is velocity, times area, pi 1.75 square over 4. And this gives 24.1 cubic feet per second. And since the question also asks GPM, we can directly multiply it by 449. And it gives 10,800 GPM. Okay, let's continue with question 5.18. And we have a rectangular channel. It has a width of 1.2 meter, and we need to find the discharge in the channel. So normally, to calculate the discharge, we are using this continuity equation, which is Q is equal to V times area, velocity times area. But here, as you can see, the velocity is not constant. So we have that velocity profile, which changes from bottom to the top. Therefore, I will say changing velocity. So since the velocity is changing, we cannot use this equation directly. So we need to apply integral form of flow rate. And you can also get more information about this the equation on slides lecture 9, page 4. So the integral form of flow rate is Q is equal to and let's say this is from initial depth and this is final depth. So for our case, starting from 0 and going to this distance, And again, we will have, of course,
velocity and area. And since we are dealing with infinite small objects here, we are using dA. So let's continue. So we will have y0 and yf. Velocity will be y to the power of 1 over 3 meter per second. And the area will be, again, we are going to use width times, I can actually show it here. We are going to use width times this height. And again, since it is infinitesimal, we are using this term to refer this height. So the area, dA, will be y times dy. Sorry, w times dy. So width is 1.2. So we have 1.2 dy. So if we integrate this, and if we leave this alone, we will get 1.2, and we have y to the power of 1 over 3. So it will be y to the power of 4 over 3 divided by 4 over 3. And this should change between the bottom and the water surface. And now we are required to find this distance because the velocity and the flow rate will be changing through this distance. So to calculate that, we need to find this distance. So this will be same with this one. And let me use some geometry here. So the angle relative to the horizontal line, this one, is 30. And since we have this vertical depth and this horizontal line, this section will be 90 degrees. So we will have perpendicular. So this section is 60 degrees. We have 90, and we will have 30 degrees. Let me zoom in. So we are trying to find the value here, which is the distance of y. So in that case, cosine 30 will be equal to d over 1, because the vertical depth is given as 1 meter. So d will be 1 cosine 30. And so d is equal to 0.866 meters. And from here, we can get this final version of the calculations. 1.2 over 4 over 3 times y to the power of 4 over 3, which changes from 0 to 0.866. So when we use 0, we will likely get 0 here. And the only thing we need to do is substitute y with 0.866. And once we do that, we can get flow rate as 0.743 cubic meter per second.
Okay, let's continue with the third question. This is question 5.20. So here we have a water from a pipe, and it is diverted into a weight tank for exactly 1 minute. So we have T as 1 minute or 60 seconds. The increased weight in the tank is 80 kilonewton. So the weight increase will be 80 kilonewton, which is 80,000 Newton. And we need to find the discharge in CMS or cubic meter per second. So let me write CMS. So we have specific weight. This is given for 20 Celsius degree. Okay, so as we know, flow rate is usually given cubic meter per second or cubic feet per second. So this means this is actually velocity, volume over time. Or we can use symbols to explain this. The volume will be this, and we have delta t, which is the time passed. So here the main question is finding flow rate. So we can write flow rate volume over time. And also, as you remember from previous sections, we were calculating weight as specific weight times volume. So volume will be equal to weight over specific weight. So let me explain why I did that. This is because in the question we are required to find flow rate, but we are only given weight and time. So we need to convert from volume to weight. Therefore, as you can see with this term, we can now use the given weight. So this will be equal to weight over specific weight times let me continue from here. So we have weight, which is 80 kilonewton, but since we are also using specific weight and it is in Newton, we can use the weight in Newton form. So we have 80,000 over, we have specific weight, actually let me write this here. So we have 80,000, we have specific weight, and we have time, which is 60 seconds. And this gives Q as 0.136 cubic meter per second. Okay, let's continue with 5.39. Here we have a gas chamber, and gas flows into and out of the chamber as shown here. Further conditions shown, which of the following statements are true? So we have 5 different statements and we are going to determine if they are wrong or correct. And the main focus is the application of the control volume equation to the continuity principle. So this means that we are going to apply continuity principle but for this control volume. So first, let me determine our control volume and control surface. So this will be our control volume, and this is the control surface. So this means this actually shows the change in this control volume. So we have inflows from this control surface, and we have outflows from this control surface as well. And this entire area is control volume. It means we are applying our principles or equations for this volume only. So we also given some values. So we have velocity as 5 meter per second. We have area 0.2 square meters, and we have density, which is 2 kilogram over cubic meters. And on the inflow side, again, we will have velocity, it is 10 meter per second. We have area 0.1 square meter, and we have density 3 kilogram per cubic meter. So you can follow your slides or textbook to apply continuity principle. So you can check page 165. It's actually starting in 164, but you can see the final version of this continuity equation, and also you can find it from your slides. So we will have this equation. dB closed system change over time is equal to d over dt. In the control volume, we have B, rho, and volume, plus we will have control surface, rho, B, velocity times area. So first, let me explain what this equation means. So here we have rate of change of peripheral to B in the system, in this closed system. So here we are going to deal with mass. And in the second part, which is here, this is the rate of change of peripheral to B in control volume. And finally, this is the net outflow of peripheral to B through control surface. So this is net outflow. This is rate of change of B in control volume, and this is the rate of change of B in system. Okay, so here the big B is extensive property, and B, the small one, is intensive property. So usually B is B over mass, and since here we are dealing with mass, because it is the main property here, B will be equal to 1. So let's focus on these statements. So let me get started with the first one. The statement A says B system is equal to 0. However, since there's a flow in this control volume and in this system, we cannot say B system is 0, because since there's a flow, there will be a mass. So this statement will be wrong. The second one is the change of property B in the system over time is 0. And we will get back to this one later. The third one says the sum of B raw velocity times area is 0. So actually, if you look at this side, it is talking about this term of this equation. So since this gives net outflow, we need to find net outflow of property B through this control surface. So we can show it with mass flow rate. This is M with a dot. And as you can see, we have rho VA and B, but as I mentioned, it is going to be 1 for this case. So M out, which is 0.2, will be rho velocity times area 2. So inflow in mass flow rate will be also rho VA, but this is 1 because this is the inflow and this is the outflow, so that we are using 2 and 1 to show these mass flow rates. And from here, out mass flow rate will be equal to, we have rho, which is 2 kilograms per cubic meter, times we have velocity, which is 5, and finally we have area, and it is also given as 0.2 square meter. And this gives 2 kilogram per second. So if you look at M in, this time we will be dealing with the point 1, which is inflow. So we have rho as 3. We have velocity of 10. And we have area of 0.1. So this gives inflow is 3 kilogram per second and outflow is 2 kilogram per second. So this term, which is the net outflow, it is out minus 1, because as you know, when we are dealing with change, we usually do final minus first, or out minus in. So it will be outflow minus inflow. So it is 2 minus 3 minus 1 kilogram per second. So briefly, this says that the net outflow is -1 kilogram per second. Therefore, here it says the total mass flow rate or net mass flow rate is 0, but it is wrong because we already calculated it as -1. And we can also focus on E, and in E it says B is equal to 0. I already explained that it is 1 here in this case, but also if it was 0, we would have 0 here, and we would have 0 here. So everything will be 0 in that case. However, we already have flow, inflow and outflow, so that we cannot say B is 0. So this is also wrong. Okay, and now let's look at B and D. So D says, D is coming from this term, and as I explained, this is the rate of change of B, or mass, in control volume. However, we already calculated the outflow and inflow. So basically, as I mentioned, this shows the flow through control surface. So this means that we have inflow through this control surface, and it impacts control volume here. And we have outflow again through the control surface. So we can say that the rate of change of B in control volume is not 0. Otherwise, it would be steady if it was 0. But in reality, we have mass flow rate changing with time, so that we cannot say the rate of change of B in control volume is 0, because as we calculated here, it is changing by time. So this is also wrong. So the only remaining term is only remaining statement is the rate of change of B in the system is 0, and let's see if it is correct or not. So if you look at equations 5.26 and 5.29, you will see that we will have continuity equation, and we will have law of conservation. And it says that in a closed system like this one, the mass over dt, so rate of change of mass over time, is 0. So basically it says that the change of mass in a system is 0, so it is constant. So here this can be confusing, because we already calculated that the rate of change of mass in control volume is changing, and also we have net outflow as -1. So this means we have inflow and outflow, or in other words, we have changing mass flow rate. But the critical point is these are happening in control volume and through the control surface. So it is only affecting this control volume. So we have change of mass within control volume, but since this is a closed system, the mass will be constant. Therefore, we are saying that this is the only correct statement. We have pistons, and these are moving to the left. So we have one piston and we have another piston here. So that this means we have a movement from right to the left, and we also have another one to the left. So we have two pistons, they are going to left. Piston A, which is this one, and this is B. Piston A has a speed twice as great as that of piston B. So this means that velocity of A is double of velocity B. And we have velocity B here. So is the water level in the tank is rising, not moving up or down, or falling? So we need to find if this water level is going down, going up, or stays at the same level. The diameter here is 3 inch, and diameter here is 6 inch. So again, for this question, we are going to use continuity equation, because we have in and out, so that using continuity equation we can calculate the final equation, because in the continuity equation we have this term, you may remember from this from the previous question. So this is a rate of change of B in control volume, plus as the second term we had net outflow, and I will directly write the change of mass flow rate. So we had out mass flow rate and in mass flow rate. So according to continuity equation, this is equal to 0, and you can find this in 5.28 and 5.29. If you remember in the third question, we had dB system over dt was equal to 0, and this term was equal to these two sum of these two terms, so that we can directly apply this equation. And you can also check for more information about continuity equation and its derivations. Please check 5.28 and 5.29. So let's continue with the question. Here we need to find water level in the tank, so that it means at some point we need to calculate something for dH over dt. So this is actually rate of change of water height over time. So the main focus for the solution will be finding this term. Okay, so let me write what we have. We have out, we have in, and this will be equal to minus d over dt rho d volume, and the mass flow rate is rho v area but this time for in, and this is equal to, and we can move this density to outside of the equation, so we will have minus rho d over dt volume. So here we can actually cancel out these row terms because they are same for all. Okay, so we have VA, which is actually flow rate of outflow and inflow. And actually let me write. So when we say out, this is actually A and this is B, because you can think this system as we have inflow from this side and we have outflow at point A. And also there was a relationship between A and B. So we have VA is equal to 2 times VB. So here, instead of velocity of A, we can directly write 2VB. And also, the diameter of B is double of A. So we can also write something like area of A is an area of B. Here actually this is diameter 3 and this is diameter for B. So since again we have common terms, we can just ignore them. So the relationship between area of between A and B, area of A is 1 over 4 area of B. So we wrote everything in terms of B. So our calculations will be easier because we just discarded A and we can get VB from this equation. So we have 2VB, which represents VA, times we have area of A and it was 1 over 4 AB, minus VB and AB. So from here we can get VB AB over 2. Minus VB AB. And this gives, we have 1 over 2 minus 1. Minus 1 over 2 VB and AB. So this was actually equal to this term. So both of them are in negative sign. So we can just replace their places. So we will have d over dt volume is equal to 1/2 of VB and AB. And let me increase this. So we have volume and it is area times height. And we can actually write this in area times dh over dt. So as I mentioned at the beginning, the focus is finding this term dh over dt, and we already did, and this is equal to 1 over 2 VB AB. So here the area will be positive, and this term is also positive, and here the velocity is positive because it is in the same direction. We are not calculating something in the reverse direction. So we have positive, therefore dh over dt will be also positive. So this means that we will have a rise in this water level. So let me summarize the question from the scratch. So in this question we had two pistons, and both are moving to left, as you can see here and here. So we use this continuity equation. Please don't get confused because this is also continuity equation as we seen in the previous equation. They are all same, but I just wrote this outflow and inflow equations. So we have out mass flow rate and in mass flow rate, and we have the change of B in control volume. Here there was a relationship stated in the equation. VA is 2 VB, so we just replaced VA with 2 VB, and also the diameter of these pistons were given. So based on that, we also find the relationship between areas of A and B. And finally, we wrote the volume as area times H. So since A is constant, which is area is constant, we can move it to the outside. So we obtained A times dH over dt is equal to half of VB and AB. So these are all positive, this is also positive, so we said dH over dt is positive. It means there is a rise in water level. Okay, let's keep going with question 5.49. Here we have two streams discharged into a pipe as shown. So we have stream 1 and stream 2, and they have flow rates of QB and QA. The flows are incompressible. The volume flow rate of stream A into pipe is given as 0.01 T cubic meter per second, and flow rate of B is 0.006 T square cubic meter per second. And here T is in seconds. The exit area of the pipe is 0.01 square meters, and we need to find the velocity and the acceleration of the fluid at the exit at t is equal to 1 second. So basically, since we have two flows as QB and QA, they will be equal to Q exit. So let me write Q exit is equal to QA plus QB. And in the question we need to find the velocity at the exit. So since V is Q over A, we can directly write something like this. V exit is equal to 1 over area. So we are basically dividing entire term by area. QA plus QB. So we can get 1 over 0.01, and we have 0.01 T plus 0.006. t squared. And these are all in cubic meter per second. And from here, t is given as 1 second, so that we will get 1 t meter per second, and it's coming from these I cancel each other out, this one and this one, plus now we are dividing this 0.006 to 0.001, and this gives 0.6 t squared, and this is actually velocity term. So since t is 1 second, we will have 1 plus 0.6. This is also 1. You'll get 1.6 meters per second. So we need to find acceleration now. The flow is incompressible, so unsteady term is 0. So this means, since this is incompressible, we cannot compress it, and there will be change in velocity, so that we will have acceleration. So if you remember from last week's homeworks, we were calculating acceleration like the partial derivative of v over t plus, and this was the local acceleration, and this was convective acceleration. And here the velocity is varying with time, so we need to use this term, but it is not changing with position, so that there will be no convective acceleration. We will only have change over time, not change over location or distance. So that the only remaining is partial derivative of v over t. So as the velocity, we had this term 1t plus 0.6 t squared. So if you take the derivative of this term with respect to time, with respect to t, we will get 1 plus 1.2 t. And since this is acceleration, it will be meters per square second. And also t was 1 second, so we have 1 plus 1.2, 2.2 meters per square second.
This is question 7, 5.75. So the question says that how long will it take the water surface in the tank shown to drop from 3 meter to 50 centimeter? So briefly, we have a water depth which is 3 meters, and this is h, and it should drop from 3 meters to 0.5 meters. So to do that, again, we are going to start with the continuity equation, because this problem involves time and a defined initial state and a final state. So applying continuity principle will be actually helpful for our case. So from equation 5.28, you will see the general form of continuity equation. So it shows that d over dt within control volume rho dA plus, now through control surface rho v d area is equal to 0. So in other words, as I mentioned, This is the rate of change of the property within control volume. And this is the net outflow through control surface. And you can also check example 5.6 because they are following same approach but with different values. So let's get started with the first term. Here we have mass, and as you can see, mass is density times volume. And here we can use rho for density. We can use area times height. So the area will be pi d square over 4 times h. We need to differentiate this term with time because it's coming from the continuity equation, so that we will have dt rho pi d square over 4h. And as we did in one of the previous questions, we actually need to find dh over dt because it shows the rate of change of water height over time. So we can modify our equation like this. Rho pi d square over 4 and dh over dt. So this is our first equation, and it is showing the first term of this continuity equation. Now we can take the second term, which will be the net outflow. In other words, it will be mass flow rate out minus mass flow rate in. So as we can see, there is no inflow here, but we only have outflow. So we can just ignore this inflow. And also I want to draw the control volume. So this is our control volume. Okay. So we only have mass flow rate out. So we have outflow. And if you take the term equation, it will be rho v area. So mass flow rate is equal to rho velocity and area. This will be density times velocity. And velocity is given as 2gh times area. So we have pi, we have d, which is 3 centimeters at this outflow. But for now, let's write d square over 4. So basically we have diameter for outflow and diameter for this tank. So this is T and big T, and this is small one. And even if the velocity was not given, we can calculate it using Bernoulli equation. So let me do a small calculation for that. So for example, if we take this point and this point, as Bernoulli, and let me write Bernoulli between 1 and 2. So we have P1 V1 square over 2G plus Z1. And if you look at it, both of them are open the atmosphere, so we can remove pressure terms. And also if you take this point as the reference, and this will be 0 and this will be 3, we can say Z2 is 0. We only have 1. And since this is a very large tank and it is at the surface, there will be no certain velocity, so it is negligible. So we can also remove that. So from here, and this was actually h. So from here, V2 square is equal to 2gh, and we can also say V2 is equal to square of 2gh. And this is the exact same value which is given in the question. Okay, now we can continue the solution. And let's say this is the second equation. So we have equation 2 and equation 1. Equation 1 is coming from the first term, and the equation 2 is coming from the second term. So if we substitute everything into this main equation, so let me write equation 1 and 2 in main equation. So we'll get rho by d square over 4 dh over dt. And if we move this term to the other side, it will be negative rho 2gh by d square over 4. So here we can directly eliminate some terms because we have them in both of the sides. So for example, we have rho, we have pi, 4, and we can keep others. And from this equation, we are going to get 2 square over capital D over the small d. So we just move these here. dh over dt is equal to minus 2gh in square root. And let's continue with that. So we can apply separation of variables so that we will keep h terms on the left hand side and t terms on the right hand side, and then we are going to integrate these terms. So we can get, let's say, ho and hf. This is final, this is initial state. So initially it was 0 meter, and final the final height will be 0.5 meters. And right now we have dh over sorry, dh over 2gh, and since it has negative, we will also have negative here, and this will be equal to, this time we are going to use t, so it is coming from initial time and then final time. So this time we are moving this to right side, and we can say it is d over capital D dt. And if we integrate this equation, eventually we will get 2h0 So this is what we are getting after taking integrals of these equations. So you can work on coming from this to final calculation. So in the question we are asked to find how long will it take. So we can leave the time term alone. So the final time will be times okay, so this is the final version of all of these calculations, and we are just going to use values we have, and then we will get the exact time. So let's see what we have. The time will be equal to the d is 0.6 and the other d is 0.3. So this is what I'm talking about. We have the diameter of tank, and we have diameter of this pipe. This is 0.6 and this is 0.06 and this is 0.03. And we have 2. We had parentheses here. So we have 2. So we have initial height, which is HO, is 3 meters, because the water is dropping from 3 meters to 0.5. And this will be 0.5 over 2g, which is 2 times 9.81 meter per second. And this is going to give 185 seconds. So this is the time that is required to drop the water level from 3 meters to 0.5 meters, which is almost here. So it takes 185 seconds. And I actually also want to show how we calculated this one. So I mean how we take integrals of this equation and we update this one. So first let me copy this part. So this is final and this is initial. So we can actually write this part like 1 over square root of 2g because it is constant and we can move it to the outside. So we will have HO and HF, and we will have 1 over square h. So this actually means h to the power of minus 1 over 2. So let me write it like that, dh. And the integral of this section will be, after writing this, so we have h to the power of minus 1 over 2, and we are increasing it by 1, so that we will get h to the power of 1 over 2 over 1 over 2. So in other words, it gives 2h square. Sorry, 2 square root of h. And since this is within HO and HF, we will get minus 1, 2g, and 2 HF minus HO. And the remaining part is this one. Sorry. And to get that, we are just multiplying it by t because we are taking integral. So briefly, this is going to be we just applied this minus sign into this HF and HO, and then we can get the same value, same equation here.